We meet again for the third time, and this time I'm going to take up the signals and systems for you. And this is a continuation of 101, taking it slightly higher level than the 101. And we'll cover the signals and systems in a more detailed manner. First, we must understand what is the signal. By this time, I am sure you know what is a signal. Some at least you have feel for it. You did it 101. You call a voltage waveform as a signal, a current waveform as a signal. But there are umpteen number of signals in the world in which you have to deal with biological signals to find out the health of the body, or seismic signals to find out whether you're going to get an earthquake or not, or signals and sea level to see whether some islands are going to be washed away or not. An umpteen number of signals which all collected in the world but I can't see them other way. So please correct me if you can't hear it, please tell me. Because I have to adjust my level of the voice for that. Okay, so we have umpteen number of signals, and as electrical engineers who contributed a lot in the signals and signal processing, we have a responsibility to learn a lot more about various possible signals and how do we handle them. In fact, our greatest contribution as electrical engineers has been our ability to deal with very, very low signal to very, very high signal, very slow varying signal to very fast varying signal, and umpteen number of signals, and make some sense out of the signals. This is where our contribution has come from electrical engineering, and it has enriched all science and engineering disciplines by our contributions. And we should be proud of it. So we should know how we electrical engineers have been able to build up this knowledge of signals and systems to be able to bring the mankind to where we are today. Without us, we would not have been where we are today. Let me be very clear about it. And so with you as young people who will do more than what we have done, you need to know something more about it so that you contribute a lot more than what we have been able to do. Okay, what is a signal? A signal is a function of some variable. That is the finest definition that we could think about. And the variable in general, conceptually we think is time. But it is not necessarily the time. It could be space, it could be pressure, it could be velocity. That could be the variable. As a result of this variable, some parameter is changing. So the relation between this variable and the function of the parameter that is varying is a relation. This relation is what we call as a function, and this function is what we call a signal. And signal mathematically is actually a function, and I am sure in your mathematics courses in linear algebra and all those things, you understood what a function is. So strictly speaking, all the mathematics you have learned in linear algebra is applicable to what we are going to do here. And only thing is, linear algebra people will talk in mathematical terms, not worrying about the physical world. And what I would like to do is to convert that into physical language. And in the process, I will do some rigor out of mathematicians, but it is more of an application orientation, but not at the level of utilitarian part of it. I am going to give you some ideas about it, some fundamental ideas, but not as a person who just applies these ideas, but not on the other hand as a mathematician who is only worried about whether the signal has a discontinuity and what kind of discontinuity is there, and I am not bothered too much about it, but we will discuss with that spirit. But remember, this is a contribution of mathematics which made us what we are, and it's good that you are learning mathematics and you have learned mathematics to be able to appreciate what I am going to talk. Okay, so signal is basically an F and this dot is the variable, and we call this, mathematicians call this domain, and they call this f as a range, right? So all the languages, let us forget about it, but for the time being, let's assume that this will represent some variable, and the relation between this variable and this parameter is what we call as a signal. And most of the signals we deal with are dynamic signals, so invariably this dot happens to be a time, because we are worried about how the evolution takes place in terms of as the time passes. So one parameter definitely is a time, but as I said, it's not necessary that this has to be time all the time, because again I'm using time 2 times, but you understand it. It could be space, for example. When you are sending an optical signal, this optical signal at this point is different from the optical signal at that point. So the relation between the optical signal from this point to that point is now variable, is a space variable, not necessarily a time variable. On the other hand, the time if the optical signal is varying with respect to time also, it will also depend upon time. So in general, they not necessarily dot represents only one variable, it may be multitude of variables. In which case this will call it a multi-dimensional system, where we have many variables which are representing the physical variables, either space or time. So in general, for example, electromagnetics, when you set electromagnetic wave, the electromagnetic waves at any point in space will depend upon the position as well as the time. In which case there will be 4 variables, right? And this function also need not be a scalar function. It could be a vector function, in the sense that if I want to measure the electric field at this point, as you know, this is a 3 component, X component, Y component, and Z component, right? And all the 3 components vary from spatial point to spatial point, and also vary with respect to time. So you have 3 components which are F, varying with respect to the 4 dimensions, which are the space as well as the time. So we have complicated signals like this. It's a multi-dimensional signals, vector signals, and we have to deal with all of them. And these signals may be homogeneous, may not be homogeneous, may be linear, may be all kinds of descriptions that will go along with this kind. So this is basically what we are going to deal with. Now if you take a signal, can you see what I write here? No. Is the size enough? No answer.
Yes, sir.
Yes or no?
Yes, sir.
Yes, good. You have saved my life. So first and foremost, this F or as a signal. Let's take one dimensional signal as a function of time, because we are more familiar with. And this may be a function which has no discontinuity. We understand mathematics, what is the discontinuity? There may be no discontinuity, or it may have finite number of discontinuities. Okay? So the function may be something like this without any discontinuity, or it may be a function like this without some discontinuity. And you know what discontinuity means. Also, this function may have well-defined derivatives at every point of time. So, if a function doesn't have discontinuities and has all possible derivatives of any order at every point, then we call this a most respectable function. My mathematics teacher used to say, this is the honest, patriotic, well-behaved function. So, such functions are very rare, but that's the most ideal function, where you have no discontinuities and all derivatives of all order exist at every point, okay? But most signals unfortunately are not of that kind, but this is the kind of a signal. So signals with finite number of discontinuities are signals with no discontinuities at all and very respectable, well-behaved, honest, patriotic functions. Okay.